The way I like to introduce the topic of transformations on absolute value functions is to describe it as a modeling situation. Previously in this class, we only discussed linear functions and lines of best fit, regression analysis. Now also behaviors in real life can follow an absolute value function. Just look at this laser being reflected off the surface. The first thing I like to do is have students graph the parent function f of x is equal to the absolute value of x. And when they put the points down on this coordinate plane, I like them to notice the slope, up 1 over 1, up 1 over 1 on the left-hand side, up 1 to the left 1, up 1 to the left 1. Now also notice the coefficient that's in front of the absolute value function. It's 1. That corresponds to the slope, which we'll see later on in the lesson. Next, I only have them change the a parameter, the number that's multiplied by the absolute value of x. I have them graph f of 2x, and then I have them notice the slope here. Now, if you look at the v shape here, up 2 over 1, up 2 over 1, up 2 to the left 1, up 2 to the left 1. I ask students what happened to the graph. Did it get narrower or wider? What was the slope? And I have them match it up to the slope that's in here. Now also, then I have them graph 0.5 times the absolute value of x. I ask them what happened to this function when compared to the parent function. Did it get narrower or wider? Well, they notice here that the slope is up 1 over 2, so this function got a little bit wider. Next, I take those a coefficients and I make them negative, and ask the students to observe what happened there. And they notice that they flipped over the x-axis next. Then I take care of the parameter that's inside the absolute value function. I have them graph the absolute value of x plus 1, and by filling in this input-output values table. I also like to question them about the contradictory phenomenon that occurs here. Although they see x plus 1, normally when someone sees x plus 1, they think the graph is going to move to the right, but what actually happens when you're applying these points, the function here moves to the left. Similarly, we notice a contradictory experience here. When we have x minus 2, we anticipate, since we're subtracting 2 from the x, that it'll move to the left, but what actually happens when you plot the points is that it moves to the right. Next, we changed around the k parameter. This one's an easy one for students to understand. When they see the minus 3, they see the graph shift down. When they see the plus 2, they see the graph shift up. Next, I have them mix up what they know about h and k and put it together. So we keep the slope of the g of x, a function that we're trying to get. We keep the slopes here 1, the a coefficient remains 1, and simply ask them to describe the movement of the vertex when compared to the parent function f of x. What's the coordinate of the vertex and what's the line of symmetry? From the coordinate of the vertex, we could tell how this function should look. Since it moves to the left, we should have an x plus 4 and then a minus 2 here. I also like to question them whether they see what they see in the formula and how it's the same to what they see in the coordinates of the vertex. So for example, the coordinate of the vertex is negative 4, 2. They see that they have to switch the x coordinate from negative 4 to positive 4 in the way the function looks. In the way you write it, it should be x plus 4 minus 2. Next, I have them try one out on their own. Then we go to a situation where now you have to figure out the a parameter. The function that we're trying to get the equation of gets a little bit narrower. I ask the following questions that you see here. So we still have to know where the vertex moves, so we can put down values for h and k. And then I give them two options. You can look at the slope, which is down to across 1, or you could plug in a point that's on the g of x for x and y and solve back for a. They should match. I make them do both methods. Then I have them try one out on their own. Next, I give some application problems where they have to write the equation of something that happens in real life. So for example, the shrub protector is in the absolute value function shape. Write the absolute value function here. So they can do this by slope or picking a point on the absolute value function. Then we have this interesting pool problem where we write the equation of the path of the ball and then predict if it's going to go in this hole right here. So they usually pick the input-output values here to solve for the a, and then later on in the problem substitute negative 5, 0 in to see if that's a solution. And this concludes my presentation of how I present absolute value functions.